All right, welcome. Today we're going to roll up our sleeves and really dig into a classic problem from Irodov's collection. It's problem 1.57, the one about the rolling cone. Now, I know these can be intimidating, but trust me, once you see the logic, it's incredibly satisfying. So let's get into it. Okay, so right off the bat, this problem tries to trick you. You see the words uniform rolling, and your brain probably jumps straight to constant. No change. And if there's no change, there can't be any acceleration, right? Well, it's not quite that simple. That's the little paradox we're going to unravel today. So here it is, the problem in all its glory. Now, the two phrases you absolutely have to lock onto are rolls uniformly and without slipping. These aren't just descriptions, they are the fundamental rules of the game. They give us the physical constraints we need to figure out not just the angular velocity, but also that tricky angular acceleration. Before we even think about writing down a formula, the most important thing, and I can't stress this enough, is to get a really clear picture in your head of what's actually going on. If you can't see it, the math will just be a bunch of symbols. So just take a second, picture a cone. Its very tip is pinned down to a table, and it's rolling. What's happening? What path is the bottom circle of the cone tracing out? How is the whole object moving through space? Really try to build that mental model. Let's break it down piece by piece. First, the tip, point O, isn't going anywhere, it's fixed. As the cone rolls, that big circular base of it actually traces out an even bigger circle on the floor. That means point C, the very center of the base, is moving in a perfect circle with a steady speed, v. This cool wobbling motion where the cone's main axis sweeps around like a spinning top, that has a name. It's called precession. And now we get to the secret weapon for this problem. This is the one big idea that takes this complicated precession and makes it incredibly simple to analyze. It's all about something called the instantaneous axis of rotation. So what on earth is that? Well, imagine you could freeze time for just a single instant. In that frozen moment, all of that complex wobbling and rolling can be described as just a simple, pure rotation around one single line. That line is the instantaneous axis. And the amazing part is, every single point on that line has a velocity of 0 at that exact moment. Finding this axis is the whole game. So how do we find this magic line? We just use the clues the problem gave us. Rolling without slipping, that tells us that the part of the cone touching the ground isn't moving. It's momentarily at rest. We also know the apex, point O, is hinged, so it's at rest too. Well, if you have a straight line of points that are all at rest, guess what? That is our instantaneous axis. It's simply the line that goes from the apex, O, right down to the point where the cone touches the plane. Okay, perfect. Now that we've found our axis, we're ready to actually calculate something. Let's tackle part A and find that angular velocity, omega. We're going to start with an equation that you've probably seen 1,000 times, the relationship between linear and angular velocity, v equals omega r. Simple, right? First piece of the puzzle, v. The problem just gives it to us. It's the speed of point C, the center of the base, and it's 10 centimeters per second. Check. One down. Now for the important part, and this is where people often go wrong. What is r in this equation? It is not just the radius of the cone's base. It has to be the perpendicular distance from the point that's moving, point C, to our axis of rotation, the instantaneous axis. If you just draw out the triangle, a little bit of simple trig shows you that this distance is r, the base radius, times the cosine of alpha. So now we just assemble the pieces. We take our expression for r and plug it back into our main equation. A quick little rearrangement to solve for omega, and we get our formula. Omega equals v divided by r cos alpha. And now, for the satisfying part, we plug in the numbers. We've got 10 for the velocity, 5 for the radius, and 30 degrees for the angle. You run that through the calculator, and boom, the magnitude of the angular velocity is 2.3 radians per second. The question also asks for the angle the omega vector makes with the vertical. Well, remember, the angular velocity vector points along our instantaneous axis. And if you just look at the geometry, that axis makes an angle alpha with the horizontal ground. So its angle with the vertical is just going to be 90 degrees minus alpha. For us, that comes out to a nice, clean 60 degrees. Okay, part A is in the bag. Now let's move on to part B. And this is the one that really messes with people's heads. We need to find the angular acceleration, which we're calling beta. And this brings us right back to that paradox from the beginning. The problem explicitly says the rolling is uniform. So how in the world can there be any acceleration? It feels like it breaks the rules, but it doesn't. Here's the key. It's all about the difference between a number and a vector. When the problem says uniform, it's talking about the magnitude of the angular velocity, its speed. That's a constant 2.3 radians per second. But angular velocity is a vector. It has a direction. And as our cone rolls, that instantaneous axis is constantly swinging around. That means the direction of the omega vector is always changing. And the number one rule of vectors is if any part of it changes, magnitude or direction, you have an acceleration. So the true definition of angular acceleration, beta, is the rate of change of the angular velocity vector, not just the speed. Since the direction of our omega vector is changing from moment to moment, that d omega by dt term is not zero. And if it's not zero, then we absolutely have an angular acceleration. You can even visualize this. Picture that omega vector with its tail pinned to the apex O. As the cone precesses, the tip of that vector actually traces out a perfect horizontal circle. Angular acceleration is just a measure of how fast that vector's tip is moving around the circle. Now, the derivation is a little involved, but the result is a clean formula for the magnitude of beta. It's the quantity v over r squared, all times the tangent of alpha. So let's plug our numbers in one last time. When you do the math, you get our final answer. The magnitude of the angular acceleration is 2.3 radians per second squared. And yeah, it is kind of funny that for these specific numbers, the magnitudes for omega and beta happen to be the exact same value. Just a little coincidence. And there you have it. We did it. We've solved Irodov 1.57. Let's just do a quick recap to make sure everything is locked in. So here's everything in one place. For angular velocity, the big idea was finding that instantaneous axis. For angular acceleration, the trick was realizing that even with a constant rotational speed, a changing direction of the velocity vector absolutely means there is an acceleration.
So the biggest lesson here is that you have to be careful with words like uniform. It forces you to think in terms of vectors, which leads me to a final question for you. Where else in physics have you seen this kind of hidden acceleration? Think about a car driving around a circular track at a perfectly constant speed. The speedometer doesn't change, but is the car accelerating? I'll leave you to think on that. Thanks for joining me.